Hi, I'm David Coase, and I'm an assistant professor in the Department of Computational and Systems Biology at the University of Pittsburgh. And I'm going to talk a little bit today about the research we're doing in computational drug discovery. The big question we're trying to answer is how do we leverage all of the compute power we have and knowledge we have and data we have to make predictions about what molecules will bind a given molecular target, like the protein shown here. And particularly, I'm interested in structure-based drug design where we know the 3D structure of the target, and so we can actually think about the physical interactions between the small molecule or ligand and the protein receptor. And the general process is this funnel where we start from the vastness of chemical space, apply some efficient matching algorithms to limit that to a smaller set of compounds, and then score those compounds with respect to receptor structure, and then ultimately look at the full dynamics of the system with water and solvent and all these other things to make predictions about what will bind molecules. And then we apply these tools in a number of applied drug discovery projects. And as an alternative method of doing all this, we're also looking at generative models. So starting with matching, this is sort of equivalent to searching the internet and returning all the web pages that contain a given keyword. And so instead of a keyword, we're asking for a specific pharmacophore, which is a 3D arrangement of essential interaction features like hydrophobicity or hydrogen bond donors or molecular shape. And we've developed some of the first sublinear time algorithms so that we can put this description of molecules into an efficiently searchable index and search in less than linear time. So we can search millions of molecules in a few seconds. And we've deployed this in an easy to use online tool, Pharmit, which thousands of people use every year. But like I said, this is just like returning all the websites that contain a given keyword. In order to be useful as Google, we actually search and rank or score and rank these molecules. And in order to do that, we've been looking at using machine learning, where we take the 3D structure of these predicted molecules and predict how they bind, how well they bind, why they bind. In particular, we're looking at deep learning, which is a neural network with multiple layers. And deep learning has been very successful in a number of domains, from self-driving cars to speech recognition to playing Go, and to identifying motion from an image. And the way these works is you take your input and you push it through this neural network, and then you calculate a loss, and then just using some calculus, you backpropagate that loss through the network, so you can assign blame for getting your answer wrong to every weight in that network, every parameter in that network, and you can update the parameter accordingly, so the next time you get closer to the right answer when you see that same example. And this has been very successful in image recognition, particularly with the kind of network called convolutional neural networks, where you're maintaining the spatial relationship of the pixels of the input features as you can compute successive feature maps by applying this convolutional kernel to the image. And so we've done a number of studies on applying convolutional neural networks to 3D molecule domains. And in this case, instead of a 2D grid of red, green, blue values like in an image, we're looking at a 3D grid, where we say there's carbon here, nitrogen here, oxygen here. And what's nice about this is it isn't an explicit featureization. We aren't deciding what's important for molecular recognition. We're basically just giving a 3D picture of the molecule to the network and letting it decide what is important. And we've been working on this for a while, and one of the things that Jocelyn, my senior grad student, has done is package this all up in an easy to use, very efficient, GPU accelerated Python package, libmolgrid, which generates these molecular grids for deep learning applications. This paper was chosen as an ACS Editor's Choice paper, and it's a lot of people are now using this approach, and we just made it this much easier by developing these tools for other researchers to apply this in all sorts of different domains. Also recently, Paul and Tomohide did a very thorough analysis of applying convolutional neural networks to the protein ligand scoring problem. And as you can see here, compared to a standard empirical scoring method, VINA, the black dot, we're pretty much always doing better with the CNN scoring across the board, both for pose selection and for affinity prediction. But we're really interested in going beyond just scoring. Scoring is, you say, here's a molecule, let me know what you think of it, and the network tells you that. But we want to leverage one of the key aspects of neural networks, which is their differentiable. So that is used during training, where we update these weights by backpropagating these gradients. But if you already have a trained network that works very well, you can keep backpropagating. Instead of updating the weights, the interior of the network, you can say, well, how should I change the input so the input looks like a better molecule? And when you do this with images, you get something like this, where if you start from just a random noisy image and keep updating it till the network thinks it's its specific class, in this case a banana, then you get this kind of banana-esque thing. So it's not really a picture of a banana, but you see the essence of banana there. And so we can do the same thing with molecules. And this is something that Jocelyn's been working on, where we have these very non-physical, not real molecules being generated based on what the network thinks would be good. And we're currently looking at how to leverage these to generate real molecules and to evaluate existing molecules and to see what we can do, and also for interpreting what the neural network is doing using these back-generated molecules. But we can also backpropagate one more step from this grid representation that you see here, where it's saying, oh, the network would like less oxygen here and more oxygen here. And just go one more step onto the atoms themselves and turn this information into essentially force vectors, saying, here's how you move the existing molecule. So we're not going to add atoms or subtract atoms from the molecule. We're just going to move it around in order to make the network more happy. And so in this case, it says move this negatively charged group of the molecule closer to the positively charged group on the protein. And so we actually implement this, and we can actually optimize molecules using neural network potentials, which is what's happening here. And if you look carefully, you can see that the whole image is actually getting a little bit less red and more green, indicating the network's happier with the result. So this is actually working, and this is something Matt published in a NeurIPS workshop paper a couple years ago. Even going beyond that, just this was generating new poses of a given ligand. We want to generate entirely new ligands. And what we've been doing up to here is using a discriminative model, where we say, here's what the molecule looks like, tell me how good it is. We want to flip that around. We want to say, we're going to sample from just a random distribution, give me a good molecule with the desired properties. And the way this is commonly done with images is through a generative adversarial network, where you actually have two networks. You have a generator network that creates these new images, and then you have a discriminator, which learns to distinguish between the fake images and the real images. And by training these in adversarial relationship to each other, you actually end up generating realistic looking but completely fake images. And it's been very successful over the years, from these blurry, low quality images to these photorealistic images of completely fake, non-existent people. And we are working on applying the same thing to 3D molecule structures in the full context of the receptor. And here's just some examples from a variational autoencoder result, where we find we can sample molecules with very low chemical similarity to the original molecule, but that maintain the spatial sort of relationships in the molecule that fill the same space and look about the same that way. And so that's just some of the projects we've been working on. There's a lot more, ranging from protein structure prediction to visualization to looking at 2D representations and graph representations of molecules. But all of these methods, that's sort of the core of what the group does, is developing these new methods and deploy these new methods, are also used in applied drug discovery projects. And this is something I want all my grad students to do, is have at least one applied project. And so I'm just going to give one case study in that. This is a protein we've been working on for a while, profilin, and specifically the profilin-actin protein-protein interaction. And this interaction is important to angiogenesis, the formation of new blood vessels, and it's something we've been working on with the collaborators Dave Gao and Partha Roy. And a while back, we discovered a compound just using traditional structure-based drug design virtual screening techniques, and is an okay compound, but Paul followed up on that and did a successive follow-up screen, this time using the CNN. And he identified a few additional compounds. The two that actually worked in cells were both identified using the CNN. And you can see here, they're actually inhibiting the formation of blood vessels to the point where there's no blood vessels at high concentrations of the compound C74. And our collaborators got very excited by this compound. It's a more potent compound, and they've applied it in a number of different in vivo and ex vivo models, including on the right here, you see kidney cancer tumors, where treating with a C74 compound reduces the size of the tumor because especially in kidney cancer, it's, the cancer cells are dependent on the growth of new blood vessels. On the left are a whole bunch of assays actually in mouse eyes because aberrant angiogenesis in the eye is a leading cause of blindness in a number of different disease contexts. And here we see that this compound is stopping the formation of new blood vessels while not harming existing blood vessels. So this is actually very exciting work that we're currently continuing to develop. And finally, I just want to give a quick advertisement for the two courses I help teach. The first is Introduction to Bioinformatics Programming in Python, which is really just an introduction to programming course. It's an intro course for people who may not have had programming but are still in graduate school. But it also serves as a nice survey of computational biology techniques. And the second is Scalable Machine Learning for Big Data Biology, which is a very applied course, project-based course, and it's really focused on the big data sets that are common in the biological context. This year, we're moving it from being taught in the fall to being taught in the spring, and it's going to be a 4-credit course. All right, with that, I'd just like to say I hope to see you all in one form or another, and look forward to having a good semester. Thank you.